Good morning, Zinedine and Joshua.
Morning, sir.
How are you?
Morning, sir.
Yes. How's the going? Huh?
Sir?
Fine.
It's fine.
Yeah.
Okay. I'm just gonna wait maybe 1 or 2 minutes, then we start because I think we only have about 40 minutes, so we need to start so that we can cover what we ever want to cover. The activity that you had yesterday, that I gave you last time, are you okay now?
Yeah.
Okay. I think last time we were on number 8, right?
Yes.
Okay.
What is this?
Right, okay, we start. Number 8 says in 1969, Neil Armstrong was the first man to walk on the moon. He spoke to the Mission Control Center in Houston, USA, using a radio telephone. He also kept in contact via radio telephone with his fellow astronaut Buzz Aldrin while they were walking on the moon's surface. The conditions on the moon do not support life. There's no air, there's no oxygen, no clouds in the lunar sky. The astronaut wore space suits to maintain a comfortable temperature and pressure on their bodies and to protect them from high energy electromagnetic radiation such as ultraviolet, X-rays, and gamma rays. Right, the first question, 8.1, the radio frequency which Neil Armstrong used to contact radio frequency which Neil Armstrong used to contact Earth was 2,287.5 megahertz. Calculate 8.1.1. Calculate the wavelength of the radio waves in meters. What do we do then? We want the wavelength. So we are given frequency. What do we do?
I think you substitute the formula.
Right, which formula do we use? Which one?
Well, I used, when I substituted it, I got lambda equals speed of light over frequency.
Okay, what was the, just give the formula first. What is it?
I think it's V equals F multiplied by lambda.
By lambda, okay, yeah. Okay, then
Yes.
I'll show the solution here. That's correct. So your formula, you're going to use that one there. V is equal to F times lambda.
Yeah.
Or you can use C is equal to F times lambda, because when you speak of light, we speak of C, the speed of light. So you're going to substitute your V, 3 times 10 to the power 8 is equal to that value that you're given there, 2,287.5 megahertz. So you multiply it by 10 to the power 6 to convert the megahertz to hertz. All right. Then you make your wavelength the subject of the formula. Then you're gonna get your answer. Your answer becomes 0.13 meters. Clear?
Yes. Yes.
Right. So it's gonna be it's supposed to be 4 marks. So you've got a mark for formula, mark for substituting the velocity of light or speed of light, then substituting the right-hand side, then your answer is 0.13. Please keep your answers to 2 decimal places. Right, we move on to the next one, 8.1.2. There's a mistake here, I said 8.1.1 for the second one. Right, it says calculate the time in seconds, right, which took time in seconds, it took okay, it took for the radio signal to reach the Earth, given that the distance of the moon from the Earth is 3.84 times 10 to the power 8. All right, how do we approach this one? We need time. Which formula are we using here?
V equals D over T.
V is equal to D over T, correct? All right.
Yes.
Okay, why can't you use C is equal to F times lambda?
Because we're looking for time. There's no time.
For time, there's no time there, right? Correct. Okay. All right. Let's have a look at the solution there. 8.2. So we're going to use V is equal to distance over time. Our V, that's the speed of light, 3 times 10 to the power 8 is equal to 3.84 times 10 to the power 8, which is the value that we had, the distance between the moon that was given. Then you make your time the subject of the formula. So you cross multiply. So you're going to have the 3.84 times 10 to the power 8 divided by 3 times 10 to the power 8. Then your answer becomes 1.28 seconds. Clear? Right. When I was marking some of the people who submitted, they were using a wrong formula here, and they were getting wrong answers here. I think they didn't use V is equal to D over T. So please just watch out for that one. Clear? All right. We move on to the next one, 8.2. 8.2, we have explain why sound cannot be transmitted on the moon for 2 marks. Why sound cannot be transmitted on the moon?
It's a longitudinal wave that needs a medium to.
Right, on the moon it's a vacuum, so you need a medium for it to be able to pass through. All right, you need a medium for it to pass through. So that's why sound cannot be transmitted on the moon. So the answer here, sound is a longitudinal mechanical wave. It requires a medium to propagate. There is no air on the moon, therefore sound waves do not exist or travel on the moon. Clear? That's why also Neil Armstrong, when he was speaking to his colleague whom he was with, he used a telephone because there was no medium for the sound waves to pass through. Right, we move on to the next one. 8.3. Gamma rays are the highest energy form of electromagnetic radiation. Explain why it is dangerous for living cells to be exposed to gamma radiation. Right, so when we check in terms of frequency, gamma rays have got the highest frequency. So they've got the highest energy radiation. So it's ionizing radiation. So this radiation, it can permanently damage the cells of living tissues and cause cancer. That's the answer that I was looking for there. Clear?
Yeah.
Right, we move on to the next one. Question number 9. The diagram below shows some regions of the electromagnetic spectrum. right? We have gamma rays, X-rays, ultraviolet, visible light, missing. Then we have radio waves. So 9.1, in the correct order from left to right, name the two unnamed regions. What is short here? From left to right.
Infrared radiation and microwaves.
Right, so we've got infrared and microwaves, then radio waves. So those are the two missing. So your solution there, it becomes infrared and microwaves. Clear?
Yeah.
Right. 9.2. Describe two properties which all electromagnetic waves have in common. Two properties which all electromagnetic waves have in common. Right? What is the answer here?
They have the same speed in a vacuum.
Right, so they all travel at the speed of 3 times 10 to the power 8. Right?
Yeah.
They travel at the same speed in a vacuum. Then the second one, they consist of vibrating electric and magnetic fields. Right? So they've got two planes at 90 degrees to each other, electric fields and magnetic fields. Any other one? Joshua, I think in your answers you added another one. What was that again? Joshua?
What is? I don't have the same stuff as the thing I put. What is as I
Okay.
don't. But it's the same. What is the speed? What in the predictions?
Okay. All right. There's someone who added something there. Okay, but it's fine. Let's move on to 9.3. Describe the relationship between the energy of the radiation and its frequency. Relationship. So we need the relationship here. So you go to your formula. Let me just see if I can open the formula here. Here's the formula. So you've got E is equal to H and H multiplied by F. So the higher the frequency, then the higher the energy. So they are directly proportional. The second equation that you have also E is equal to HC multiplied by wavelength. Then what you're going to have the bigger the wavelength, then the smaller the energy. So you need to use these equations here and check which one is the numerator, which one is the denominator. So E and F, they are both numerators, so they are directly proportional, and H is a constant. Then you've got your E and your lambda, they are inversely proportional. So when one increases, the other one decreases, right? So wavelength is inversely proportional to energy. The bigger the wavelength, the smaller the energy. Clear?
Yeah.
Right. So back to that relationship, the answer that I was looking for is this one here, right? Which says the energy of the radiation is directly proportional to its frequency. So they're directly proportional. Right. We'll move on to the next one. Question number 9.4. Calculate the energy of a photon of visible light with a wavelength of 180 nanometers. And you must know nanometers there. 1 nanometer is equal to 10 to the power 9. Remember what we did? We said kilo 10 to the power 3. We have got mega, it's a 10 to the power 6. Right, then we've got giga 10 to the power 9. Then we've got tera 10 to the power 12. When you go down, we've got milli 10 to the power negative 3. Then we've got what's the other one there? We've got micro 10 to the power negative 6, nano 10 to the power negative 9, and we've got pico 10 to the power negative 12. Please don't forget that. It's not that always you'll be given those. Yeah, they expect you to know that. So here, calculate the energy of a photon of visible light with a wavelength of 680 nanometers. So the calculation here, we need the energy, right? So we're gonna use the formula. The formula that we use is E is equal to, okay, you can use, there are two ways to calculate this, right? You can start by calculating the frequency, right? By using the formula V is equal to F times lambda, right? You substitute V, speed of light, 3 times 10 to the power 8, and you substitute the given wavelength, 680 times 10 to the power negative 9, then you get your frequency. So it's going to be 3 times 10 to the power 8. You divide by the wavelength. Then your answer becomes 4,41 times 10 to the power 14 hertz. Now, the question wanted you to find the energy. So you're going to go a step further. Then what you're going to do, you're going to substitute E is equal to HF. Now that you've got your frequency, you substitute it there. And your H is a constant, which is Planck's constant, which is 6,62 times 10 to the power negative 34. You multiply that, then you get your answer 2,93 times 10 to the power negative 19 joules. Clear? Right? Or if you want, you can just use the one formula, then you substitute everything in that. So you don't have to find frequency. You don't have to find frequency, you just go straight. So E is equal to H, your Planck's constant, your speed of light, 3 times 10 to the power 8, and your wavelength, which is converted to meters from nanometers, then you get the same answer. Clear?
Yeah.
Right, we go to the next one, please. If you don't understand anything, you can ask. We go to 9.5. X-rays are used to diagnose bone fractures as well as to investigate how the lungs are able to function. Right? Ultrasound is used to diagnose conditions of the internal organs. For example, the kidneys, liver, the development of the fetus during pregnancy. All right? 9.5.1, give two differences between ultrasound and X-rays. Right? Okay, let's check on the answers here. Ultrasound is a longitudinal wave, and the X-ray is a transverse wave. So that's the difference in terms of the type of wave. Right? Or what can you say? You can say ultrasound travels at a lower speed than X-rays. X-rays, they travel at the speed of light, which is 3 times 10 to the power 8 meters per second, 300 million meters per second. And ultrasound, it's less than that. That's another difference. Next one, you can say ultrasound do not damage soft tissue. X-rays, they do damage the living tissues. That's why when you go in the X-ray room there, they make you wear some jackets to protect you so that the X-rays, they don't damage your tissue. All right, then ultrasound waves, they transfer less energy as compared to X-rays. So the ultrasound is safer than X-rays. Clear? Right, then we move on to the last question here. It says, why is ultrasound safe to use as a tool to investigate the development of the fetus during pregnancy, but X-rays are not? Right? So what do we do here? How do you explain this? You're gonna say, ultrasound waves do not damage soft tissue. X-rays, they do damage living tissue. Or ultrasound waves transfer less energy than X-rays. Or X-rays is a form of ionizing radiation. So it will cause cancer, this one, or it will damage tissue for the young one. Ultrasound does not cause ionizing in the materials that it travels through. So any one of this explanation, then it's worth 2 marks. Clear?
Yeah.
Yeah. So that's the consolidation exercise that you guys had. I'm not sure if there are any questions under electromagnetic radiation.
Sir,
Yes.
can we go back to number 9?
Number 9. Okay. Number 9. Which 9? 9 point?
The one that had the formula next to it.
9.4.
9.4. Okay. Is that the one?
No, it said like or E equals H over C over something like that.
Okay, on the solutions. This one.
Yeah, that one.
Okay.
So what does the C mean there?
C is the speed of light. 3 times
Speed
10
of
to the
light.
power 8. Speed of light, yes.
Ah,
Yes.
okay,
So when you speak
fine.
of sound, when you speak of light, we use C because light travels at 3 times 10 to the power 8.
Okay.
Yes. So we're using that C for the speed of light. If it was sound, you can't use 3 times 10 to the power 8. It only applies to light.
Okay.
Okay. Right. Then we move on. Okay. Any questions here? Any questions?
Now,
Okay. Let me just see the other participants there. Oratile, any questions?
No, sir.
Oh, you're fine. Okay. Who else here? Jolisha, any questions? Okay. All right. So after this, which are the part you didn't understand on the exercise that I was sending through? Anything? Yes. Let me just check here. Okay. There's then, if there are no questions, let me just explain here. There's waves, legends, and folklores. All right. There's this part here where animals, sharks, they tend to predict if maybe a disaster is about to come. All right. So that's the part which speaks about waves, legends, and folklores. So people have believed that animals can predict earthquakes and other natural disasters for centuries, right? So it is believed that dogs and cats, maybe if a disaster is about to strike, they, some of them, they make funny noises, right? And some of them, they bite their owners, maybe just to give them a warning to start moving or something like that. Sharks, researchers in Florida have reported that sharks are observed to move deeper water before hurricanes and so on and so on. So they tend to, maybe they've got a sharp sense, they can sense disaster at a far distance than humans. Rodents as well that live underground will often flee their holes and burrows before a disaster. Right, elephants will allegedly trumpet and flee to higher ground before tsunamis and so on and so on. So this is just another part which is related to electromagnetic waves, because animals can they can sense certain waves that humans do not. So that's what we have there. Okay, then under physical change. Under physical change, I think I explained this last time. I explained this, and I posted the solution on this one. Did you manage to look at that solution for exercise 7?
Yes.
Okay. So let's just go over it quickly. We have got exercise 7, define a chemical change. What is a chemical change?
Chemical change is the change or transformation where substances are formed through a chemical reaction of one or two substances.
Right? Or to make it easier, the simple definition would be a reaction or a change in which new substances are formed. Clear? Right? So a chemical change, just say in a nutshell, you can just say it's a change in which new substances are formed. And the physical change is a change in which no new substances are formed. Clear?
Yeah.
Right. In terms of conservation of mass, molecules and atoms distinguish between physical and chemical changes. Right? Between a physical and a chemical change. So in a physical change, the mass is conserved. What do you mean by conserved? It means the mass of the product is the same as the mass of the reactants. The number of molecules in the reactants is the same as the number of molecules in the product. So molecules are conserved. Atoms are also conserved. So the initial and the final ones are always the same. Right? Okay. Then in a chemical change, please, can you just mute? I'm getting some feedback. I'm not sure which.
Unati.
Is Unati?
What did I do? I just got.
Your volume's too loud.
Just reduce your volume. Okay. Right, so we continue. We have, for a chemical change, mass is conserved, atoms are conserved, but molecules are not conserved. That's for a chemical change. So that's the difference. So physical change, mass, molecules, atoms are conserved, but in a chemical change, only mass and atoms are conserved. Molecules are not. Clear? Right, then we've got distinguish between a decomposition reaction and a synthesis reaction. A decomposition reaction, it's where you start with one, then you end up with many products. So you start with maybe one reactant, you end up with two or more products. In a synthesis, you start with two reactants and you end up with one product. That's a synthesis, to synthesize. Clear? Right? Then number 5, for each of the following, say whether a chemical or physical change has taken place. 5.1 is got melting candle wax. All right, what is that? Is that chemical or physical?
Physical.
Right, that's a physical change because the wax dries out and you still get the same wax. All right, next one, 5.2, mixing silver chloride and silver nitrate to form silver chloride. So there's a new whole complete new substance is being formed there, which is silver chloride. So what is that? Chemical or physical?
Physical.
Right, it's come again.
Chemical change.
Chemical change, correct. Next one, 5.3, mixing hydrochloric acid and magnesium ribbon to form magnesium chloride. That's a chemical reaction there because a new substance is being formed. Clear?
Yes.
Right, then the next one, 5.4, dissolving salt in water. Chemical or physical?
Physical.
Right, that's a physical change. All right, because we can still reverse that one. We can still get the salt that is dissolved in the water by evaporation or by boil. By evaporation, we can the water will evaporate. Yeah, then we get the salt. So physical changes, they are reversible. The chemical changes are they are irreversible. Or they are difficult to reverse. Clear?
Yes.
Okay. We left with 10 minutes. Then the next one, 5.5. Tearing a piece of magnesium ribbon. Physical or
Physical.
chemical?
Physical.
That's a physical change, right? So that's what you get. Then number 6, a science teacher decides to bake a cake in class to demonstrate a chemical change. Identify 2 characteristics that indicate that a chemical change took place during a chemical reaction. Right? How would you see that a chemical reaction has taken place?
Change in temperature.
Right? Change in temperature, 1, yes.
Formation of precipitate.
Formation of a precipitate, yes, that's another one. There are about 4.
Change in color.
Change in color, yes.
Release of gases.
Right, then you see bubbles being released. That would be evidence to say a chemical reaction has taken place. Clear?
Yes, sir.
Right, that's a particle nature. Then I think that's what we have so far.
Yes.
Yeah. So I'm not sure. I'll leave this remaining 8 minutes for questions, if people have questions.
During a chemical change,
Yeah.
the question in exercise 8, where they would talk about why there was different molecules and the number of atoms are conserved, but there's a different ones of molecules.
Yeah.
If it's fine to say that in the chemical reaction, new substances are made where the ratio of elements can vary, therefore creating different amounts of molecules, or is it more better to say rearrangement? There's a rearrangement of.
I think both are fine because as long as you're pointing out that the molecules are going to change, then it's fine. Both of them are correct. They are okay.
Okay.
Yes, so it's correct then. All right. Any other question?
Is there a certain format for writing to show that the mass of substances are conserved? Is it there a specific way you have to write it?
Or to write it? No, there's no specific. As long as you calculate the mass for the reactants separate, then you do the product separate, then your answers, you compare your 2 answers, then it's fine. Let's say you've got hydrogen and oxygen. So if you calculate for your hydrogen plus your oxygen, then you've got your total, right? As long as you indicate how you get those answers and your answers are correct, then it's fine. There's no specific format. As long as you're using everything that is part of that reaction, it's fine.
Okay.
Oh yeah, there's no specific format. I'm not sure, do I have an example here, or it's on the other handout here? Like this one that you have here. So you can do the same like this one that is on the screen here. It's still fine. Right? For the conservation of mass. Right? Okay. Any other question?
Sir.
Yes.
So do you know when we're going to write exams, sir? If the school open?
No, you'll be. I think you'll be told. You'll be told as to when, because I think they are trying to change, especially the content for term 2. So maybe there could be a whole lot of changes. Maybe you're not going to be writing the media exams, something like that, because they want to try to. We'll see when the minister speaks. Then I think they're going to be coming with plans as to what's going to happen.
Okay.
Yeah, for now, don't worry about that for now. And in physical science, also term 2, we don't have too much SBA tasks. It's just your June exam, paper 1 and paper 2, that's all. And they've changed. We used to have an experiment. So they removed that experiment to third term. So we are covered. So the only thing that we'll have, it will be just your June exam. If you are gonna write it, it will be just paper 1 and paper 2, that's all. So I'm not sure whether you're gonna write it. Let's wait and see what will be the arrangements. But they're trying to shift some of the work to a later date or something like that. So we'll advise once we have the information.
Okay.
Yeah, so for now, just concentrate on the content, understand what we're doing. So the next topic that we're gonna move, I've prepared a handout for balancing of equations. That's the last chemistry that we are doing. Then we move on to physics. So we're gonna start on magnetism. We go to electrostatics. Then we go to what is this? We go to electric circuits. Clear?
Yeah, okay.
Yeah, so after this lesson, I'm gonna post the topics that are remaining for the year and the ones that we've done so far. I'll post it on Google Classroom so that you can check if you have to work ahead, so you can do that. Right, guys, let's just discuss when is our next lesson. And we have it on Thursday. Thursday?
Yes.
Thursday, sir. Yes, sir.
Yeah, Thursday, same time. Is it fine, Devo?
Okay, sir.
Is it fine?
Yes.
Yes, sir.
Okay. All right. Let's have it Thursday, same time. Today, I'm going to post presenting chemical change, which is about balancing equations. We'll speak about that on Thursday. So please just follow that. Then we round up. Then I'm going to have a consolidation activity, just like it's like a test that you're going to do just to check what we've been doing under chemistry, if you understood what we've been doing. Then after that, we start with physics. We look at magnetism.
Yes, sir.
Right.
Yes, sir.
Okay. I think that's all we have for today. I don't know, are there any other questions?
So I asked you yesterday, what's the difference between relative atomic mass and formula atomic mass?
Relative atomic mass formula, it's one and the same thing, because relative atomic mass, the masses that we have on the periodic table, we use that to calculate the formula mass of that particular substance. For example, you've got your water, H2O. You're gonna check the mass for hydrogen. Hydrogen is 1. You multiply by 2. Then you check the mass for oxygen, it's 16. Then you add 2 plus 16 gives you 18. That's what we have. That becomes your formula mass, which is because we are using the relative atomic masses from the periodic table. So it's also the same as your relative atomic molecular mass or relative mass. Next.
Okay.
Yes. Just relative atomic mass, it would be for an atom, then molecular mass would be for that particular molecule. So we use the relative atomic masses to calculate the molecular mass if it's maybe not one atom, but it's a molecule. Clear? Yeah, the values that we use are the ones that are coming from the periodic table, so they're almost the same. Yeah. Any other question?
Me, sir.
Yeah.
So could we go further back where you say ultrasound?
Okay. I think we're gonna be cut out here with this Zinedine. Is it Zinedine? Sakile. I think we left with a couple of seconds. They're gonna cut, but okay. Where must I go? On the consolidation.
I don't know. So you said ultrasound with, that do not damage tissues and other things.
Okay, Sakile, please ask in first thing when we start the lesson on Thursday, because we don't have time. We're gonna be cut out here.
I will, sir.
All right. Okay. All right. So, okay, you guys enjoy the rest of your day. You can go back.